Okay. All right. Yeah, it's recording. So let's click here to pause. I'm going to pause just a moment. Okay, we are finally recording waves. Any questions before we get started? Okay. Spherical waves. As I'm talking to you now, you might think my voice is just going to you. No, it's going this way and that way and every way. People sitting anywhere would be able to hear it. Really, it's a spherical wave leaving. Okay? Spherical wave propagates radially outward from the oscillating sphere. I'm not really oscillating, but my vocal cords are. The sun's doing the same thing. It's sending rays out in all directions. We just catch a little bitty wedge of those, but it's sending them out in all directions. The energy propagates equally in all directions. Okay? Now, of course, when I talk, I'm projecting in one direction or another, but the sun is projecting everywhere in every direction. Okay? So that's doing equally in all directions. The intensity, remember how its intensity is measured? Watts per meter squared. That's the average power in watts over the area, which is meter squared. So that's the average power. And then what is the area of the sphere? Don't remember, the volume of the sphere is 4/3 pi r cubed. The area is 4 pi r squared, which to me is a pretty incredible thing. If you consider the center diameter of that's pi r squared, and then the sphere, you could fit exactly 4 of those, precisely 4 of those to cover its area. And that to me is just amazing, but it's true. Okay? So there is your intensity of a spherical waveform. Now, there's a pretty decent picture of it. Here is where the wave is R1. Sometime later it's at R2. Of course, it's moving in all directions. Much earlier it was just here, whatever that would be, or it's a -1 or whatever. Now, what is the intensity of a point source? Since the intensity varies as 1 over r squared, that's an inverse square relationship. Lots of things follow inverse square relationship. Okay, gravity does. Electric fields, I mean, lots of things that sound, magnetic radiation from the sun, all things do. The average power is the same through any spherical surface centered at the source. Okay, let's go back here. The average power coming out of here is the same there as it is here, as it is there, as it is there. Same power is passing through that. But the area of that sphere, surface area of those spheres, are getting bigger. Same power divided by bigger and bigger areas, meaning the intensity is decreasing and falling off by the inverse square law. Okay? So the average power is the same through any spherical surface centered at the source, and to compare the intensities at 2 locations, the inverse square relationship can be used. So I1, intensity at the first radius divided by intensity at the second radius is the ratio of R2 squared to R1 squared. Why is that? Because the I is average power over 4/3 pi R1 squared, that would be I1 right here. And now power is the same through every one of them. I2 would give you that same power divided by 4/3 pi R2 squared. That would be I2. That would be out here. Well, if you do the ratio, which was it, I1 to I2 or I2 to I1? I1 to I2. Let's actually do that. Okay? Like we said here, let me get my pen. Where's my pen? There it is.
This thing is so slow. It's not responding. There we go. Wait. There we go. All right. I'm going to do them on the next page. Okay. I is so slow. 1 is equal to P average over 4 pi R1 squared. I2 is equal to P average over 4 pi R2 squared. So the ratio of I1 to I2 is the ratio of these. Okay? The P average is the same for both of them, so those divide away. Suddenly my pen is not working. Let me try it again. That time it worked partly. Okay. 4 pi are the same, so they divide away. And what do we have? The ratio of I1 to I2 is 1 over R1 squared over 1 over R2 squared, which when you flip the denominator is R2 squared over R1 squared. So sure enough, the ratio of those intensities, R1 being the closer, R2 being further away, that's the ratio of R2 squared, that's the bigger radius squared over the smaller radius squared. So again, it's inverse square relationship. Inverse because they're opposite each other, but that ratio, I1 is more intense than this because this is the larger radius squared over the smaller radius squared. That's the ratio of the intensities. Okay. Now, how do we represent those waves? Well, one name is the wave front. That's where the wave is at any given time. And the wave fronts are concentric arcs. Here's a wave front, there's a wave front, there's a wave front. Okay? The distance between successive wave fronts is the wavelength. Okay? So if you have a wave here, say that's the max here, and it goes to a min and another max here, a min and another max. The distance between these is your wavelength. Okay? The rays are radial lines pointing outward from the source, and they're always perpendicular to the wavefront. All of these are right angles, always. Every one of them, always. Because this is curved, these are going out in a radial span like that. Okay? The rays are radial lines pointing outward from the source, always perpendicular to the wavefronts. The distance between the two wavefronts is, two consecutive wavefronts, is your wavelength. Okay. Now, a lot of times we treat waves as if they were planes. Well, these don't look planar at all, do they? Those are concentric spheres, the wavefronts are. But guess what? You get far enough out of here, and you can almost imagine that's a plane. And when they get even further out here, centered at that same circle, man, they really do look like planes. So if you get far enough from the source, those spherical wavefronts almost become almost become plane waves. Far away from the source, the wavefront, way out there, man, you can hardly tell that those aren't parallel planes. Here to them, but basically they're almost like planes. The rays are nearly parallel lines, and the wavefront is approximately a plane wave. Just take this little portion there, you can hardly convince me that's not a straight line, plane wave. And those rays, as you get far enough from the source, they're getting closer and closer to being parallel. They never are like, but they're awfully close. Awfully close. Okay. So let's look at plane waves. Any small portion of a spherical wave that is far from the source can be considered a plane wave. The wavefronts are planes parallel to the XZ plane. Let's say YZ plane. If you're going out the x-axis, and here's your y and z this way, then these wave fronts are plane parallel to that xy plane. If you're far enough from the source, okay, and you're taking a small enough portion of that. Again, the different distance between those are still your wavelengths. Okay? The wavefronts are parallel to the plane containing the y and z axes, and they're moving away. Okay, I think we beat that one. The velocity is along parallel to the x-axis. Sorry. It's called the wave velocity. Whoa! That was it for 14.5. Now they have an example in here, intensity variations of a source, and it's just plugging into those formulas pretty directly. If you have questions about these and want to see these done, I'll be glad to try to do those. Okay? Anyone familiar with the Doppler effect? Okay, you know what it is. Where do you see or hear it talked about some? Not quite on a daily basis, but at least once or twice a month, you'll hear somebody, usually same type people, talking about Doppler, especially during storms. Say again? Okay. You say radio? Huh? Okay, tornadoes for sure. Okay. Why do they mention Doppler effect then? They don't say effect, they say Doppler radar. Okay. No, to measure velocities. Okay? And if you've ever noticed there, when you have greens that are increasing speeds are coming toward you and reds are going away from you or vice versa, that means that somewhere there they've turned, and that means you have circulation, which could infer a tornado. Doppler radar will tell you that, because Doppler effect deals with velocities and stuff. A Doppler effect is experienced whenever there is relative motion between a source wave and an observer. Now, the classic definition of this would be, if you've ever lived or happened to be near a railway line, okay, and the train's coming, you hear it on its way. Now, a couple things are happening, and don't get these confused. Certainly, if the train's way off there and you hear the train coming, maybe if he's blowing his whistle or something else like that, you hear it's getting louder as it gets closer. That's not Doppler, okay? What Doppler is the frequency changes as it gets closer. As it gets closer, certainly it's getting louder, but also the pitch is getting higher. It's different from the sound getting louder, the pitch is getting higher. Like it's going, and then as it leaves you, you know, because the pitch is going lower. And certainly that's, you know, the intensity is changing, but what we're talking about here is the relative motion between the waves of the observer. When the source and the observer are moving toward each other, and that could be either you're moving toward the source, or the source is moving toward you, or both, then the observer hears a higher frequency. What is frequency? Frequency is, well, we'll get there in a minute. I don't want to do that. Let's go on and deal with it. Okay. I want you to think of a couple things. The velocity of a wave is equal to wavelength over period. Okay? Length over time. Okay? Now, period is equal to 1 over frequency, or frequency is 1 over period, so this would be the same as lambda times frequency, because 1 over frequency is 1 over period, okay, per second. That's what that is. And 1 over period is frequency. So this is what you got. Your velocity is related to that. Now, your wavelength hasn't changed any, but as the velocity is increasing, that makes the frequency go up, that relative velocity for you. Velocity is decreasing, heading away from you, the frequency is getting lower. Okay? Because the wavelength is fixed, it's the same. So the observer hears a higher frequency when the source and the observer are moving toward each other. When the source and observers are moving away from each other, then the observer hears a lower frequency. That's why now certainly lower intensity for sure, because it's moving away, but the frequency, it's dropping off. Now, I don't know if any of you are Big Bang Theory fans, the show. I don't see it frequently, but I happen to remember seeing one show. I guess it was a Halloween party, a Valentine's Day party, or something like that, and Shelton went dressed as the Doppler effect. His T-shirt had the wave fronts close together here and further apart, changing. And everybody said, "Well, what are you dressed as?" He said, "I'm the Doppler effect." And then he started explaining it, and they turned around and left. That's usually what happens when people start talking about the Doppler effect. Okay. Although the Doppler effect is commonly experienced with sound waves, it is also a phenomenon that's common to all waves. Okay? For instance, there's a guy named Hubble. Have you ever heard the name Hubble before? Okay, Hubble Space Telescope takes all those fantastic pictures from space. He was one of preeminent astronomers probably of all time. And he noticed that when he was viewing distant objects like galaxies, it seemed like their colors were heading toward red, meaning the frequencies were getting lower, which meant they were moving away, which came up with a whole new concept of our universe, is that things are still moving apart, And sure, the Big Bang Theory would have them moving apart for a while. The really strange thing about it, they're accelerating apart. So they're not just moving apart, they're moving apart at more rapid rate. So he used Doppler effect to determine that, because things were shifting to lower frequencies, meaning they were moving away. So it's not just sound. Light waves obey that. Now, here's some assumptions. We assume the air is stationary. Not really always stationary. You look out there, the air is not stationary, but at least it's not moving uniformly in one direction. It's going all over the place. The speed measurements, all speed measurements are made relative to the stationary medium, which we're going to assume is the air. Okay, it's not really, but there. So all speed measurements are measured relative to that. So here is a case. Here the source is fixed, the observer is moving toward the source, and if that observer is moving toward the source, the frequencies are going to go up. Why is that? Well, the wavelengths are constant, but the velocities in this direction, this velocity in that direction, the waves are coming closer together, but they hear them. She's going past this one, and then in a short time past that one, shorter than would be allowed for the wavelength to move on its own. If she was standing still, parked there, then she's going to hear one certain frequency, because her velocity is 0. But with her moving in that direction, the velocities add, you might say, the wavelength being the same, frequency goes up. Okay? Due to, she's saying his movement, looks like I heard of me, but anyway, the observer detects an additional number of wavefronts in the same time period, okay? So the frequency for it is increased, going up, okay? most of the time on a bicycle, you're not moving that fast, so you're probably not going to detect that much. I can't remember if I've mentioned bats in here. Have I?
Yes, and how blind they are.
What's that?
How blind they are.
Okay. How do they catch mosquitoes then? Yes, because of their really super sensitive hearing, and they can detect these changes of frequency. And when the frequency is getting higher, they know they're coming toward the insect. Now, how in the world their sound bounces off a mosquito, I don't know, but I'm glad it does, okay? Because the more mosquitoes they can eat, the better I feel, okay? So, that's case one. The cyclist, the observer, is moving toward the source, okay? But what if you pass the source and now are moving away from the source? Then the velocity of the wave is having to go further before it catches up to you because you're moving in that same direction. So the frequency seems to be decreasing. The wavelength's the same, but the distance, the time interval between fronts has been lengthened now, so it seems to have a lower frequency. The observer detects fewer wave fronts per second because it's moving away from the wave front, okay? The frequency appears to lower. Now this would be true whether the observer were still and the source coming to him or her, or the source is fixed and he or she is moving away from the source. Okay. So here's the equation. When moving toward a stationary source, the source is stationary, you are moving, the observed frequency, that's what the O stands for. This is not the frequency of the sound wave. That's your observed frequency of the wave. That's the actual frequency of the wave multiplied by the sum of these two velocities. Your velocity plus the velocity of the velocity of the observer plus the velocity of the wave divided by the velocity of the wave. When moving away, or the sound, when moving away from the stationary source, you substitute minus V0 up there, and then that gets less. See, this is obviously a larger denominator than the numerator than the denominator, so this ratio is greater than 1, so the frequency of the observer is greater than the actual frequency. If you put a minus in there, then the numerator is obviously less than the denominator, so this is a ratio less than 1, so the frequency of the observer is less than the frequency of the source, meaning it's a lower frequency. Okay, does that kind of make sense? Now, this time, we're going to have case 2 where the source is the thing moving, not the observer. As the source moves toward the observer A, here's observer A here, the source is moving toward him, the wavelength appears to be shorter and the frequency increases. The actual wavelength is the same, but it seems to be shorter because the wave fronts are reaching them in shorter time intervals because the source is moving. Okay? So the frequency increases. As the source moves away from the other observer B over here, then the wavelengths appear longer and the frequency appears lower. Okay? Now, here is a picture of ripples on water. Okay? To sort of illustrate this. If you notice, these fronts are closer, these are further away. So this appears to me to be moving in that direction. Okay? It says to the right, but it seems like it's down and to the right to me. Though this seems to be, so maybe it is just to the right, I don't know. Maybe it's just the way the light's playing with it. It looks like to me that's the direction of this motion. But now I can't tell, this is probably looking at these waves, I would say that's the direction. These waves, it looks like that's the direction. But somewhere in there, it's moving to the right. Because the fronts are getting closer here and further apart. Okay. Now, in this case, your frequency of the observer is the frequency of the sound. But in this case, the velocity of the wave, this is the wave velocity, but now you're subtracting v sub s here because the this now, your numerator is larger, the denominator is smaller, meaning as this is coming toward the observer, the frequency goes up. Okay? Because the denominator here is the actual speed of the wave minus the speed of the source because it's moving in that direction. And that's what gives you the difference. You're doing the subtraction off the denominator. Using the minus v sub x when the source is moving toward the observer, and plus v sub s when the source is moving away from the observer. Okay, so the gal who was sitting over here, then you use the plus vs, meaning the denominator is getting larger, numerator staying the same, so your ratio is getting less because this is getting larger, so therefore this is getting less, the frequency is getting less. Okay. A lot of similar, and almost so similar that it can get almost confusing equations, but don't let them swamp you. Just stay with what's moving and what's not, and numerator, denominator, what you're doing. You'll always have the book to look them up. Okay? Now, here's the general case. In this case, both the source and the observer could be moving. So in this general case, your F sub O, that's the frequency the observer senses. F sub S is the frequency the sound is actually making. In this case, the V, velocity of the sound, that's the same throughout. Sound, not source. Okay? V sub S is the velocity of the source. Okay. F sub S is frequency of the sound, but V sub S is velocity of the source. Okay? Both F sub S is really stand for different things. In this case, the observer is moving toward the source because the V naught is positive, is plus. And in this case, the source is moving toward the observer. And that's why you put a minus down here. So in this case, your numerator is getting bigger, the denominator is getting smaller, so the frequency of the observer is even heightened above what it was before. It's actually higher. You use positive values of V sub 0 and V sub S when the motion is toward. That is a very lousy sentence. Use positive values of V sub 0 and V sub S if the motion is toward. Okay? I guess toward one another, they need something else in there. Then the frequency appears higher. Okay? I guess, I don't know. Use negative values of V0 and Vs if the motion is away from each other. Okay? Then the frequency appears to be lower. Okay. Now, in other words, keep these signs the same, just change the sign of one or the other of these. If the object is moving toward the sound, then that's a positive. If the source is moving toward the object, then this is positive, but this is still a minus sign. Okay. So, sure enough, that one formula says it all. The Doppler effect does not depend on distance. As you get closer, the intensity increases, that's the loudness, but not necessarily the frequency. The apparent frequency will not change with distance, okay? It doesn't depend on distance, only depends on speed, okay? Velocity is the thing that has to be changing, not just the distance. Okay. And if you haven't noticed, the book and the slides are almost identical. Okay. Now, one thing that I do want to check on, I can't remember, I did this in my last class too. I couldn't remember if we had done a quick quiz. Yes, we did. We did quick quiz 14.1. We're now ready for quick quiz 14.2. Suppose you are on a hot air balloon ride. Got it? Okay. Carrying a buzzer, not a buzzard, but a buzzer that emits a sound of frequency F. If you accidentally drop the buzzer over the side while the balloon is rising at a constant speed, what can you conclude about the sound you hear as the buzzer falls toward the ground? Now, the buzzer's going off the whole time. So you're rising, the buzzer's falling toward the ground, it's going off at a fixed frequency F. A, the frequency and intensity increase. B, the frequency decreases and the intensity increases. C, the frequency decreases and the intensity decreases. D, the frequency remains the same but the intensity decreases. Which of those do you think it might be? Do I need to write them down? Because some of you still don't have books. Okay? Now, so here you are in the hot air balloon. There's the basket you're in here, and here's the balloon up here. Okay? You're going upward. Your buzzer has fallen toward the ground, so it's going downward. You're going up, the buzzer's going down. Okay? Now, A was frequency increases. Let me do it this way. Frequency increases, intensity increases. Okay. B was frequency decreases, but frequency decreases, but intensity increases. C, the frequency decreases and the intensity decreases. And D, frequency stays the same, intensity decreases. Which of those do you think would be the case? Balloon's going up, the buzzer's falling down. Say again? I couldn't hear. I can't hear.
I'm reading.
Oh, okay. C, is that what you said?
Yeah.
Meaning yes in Spanish? Yes, okay, C, okay.
Right?
All right.
That's wrong?
No, that's right.
Okay.
Because you're moving apart,
Right.
so the wavelengths are getting further apart, even though they really are the same, but they sound like they're getting further apart. You're also getting further away, so the intensity is decreasing too. So frequency and intensity are decreasing. Let's see how the back of the book did. This is 14.2. Getting closer. 14 quick quiz 2 is C. Very good, meaning yes. Okay. Now, there's an applying physics 14.2, which is out of tune speakers. There's an example 14.4, listen but don't stand on the track. 14.5 is noisy siren. If you need to see or witness any of those being done, I'll be glad to do those. Now, 14.6 is shock waves. Okay? Oh, it's 14.6.4. Okay? 14.6.3 was the general case. 14.6.2 was the source moving relative stationary observer. 14.6.1 was the observer moving toward a relative stationary source. So all this is still in 16. It's 14. This is the last section in 14.6, and this is the fourth one, shock waves. A shock wave results when the source velocity exceeds the speed of the wave itself. What do we mean by that? Well, if you remember, the speed of sound in air was approximately 330 or so. And what was that measured in meters per second? I think that was right. It was way back we did this. Goodness, I'm running out of energy. Yeah, about 331 meters per second. Okay? That's around 0 degrees. So 331. That's in the 330s. Okay? Meters per second. Well, what if the source of that sound, let's say a jet aircraft, exceeds that speed? So the speed of the sound leaving the aircraft is at 331 or 2 or 5 or something like that meters per second. What if the jet plane actually can fly faster than that? Now we have to calculate and see what that is in miles per hour to make sure it's doable, but we know it is. Okay? A shock wave results when the source velocity exceeds the speed of the wave itself. The circles here represent the wave fronts emitted from the source. Okay? So if this is your source, and here's the wavefront here, that's the S0, and S1 is, goodness gracious, my eyes are aching, is this wavefront. S2 would be this wavefront. S3 would be this wavefront. Keep on going down. At Sn you get here, and if you'll notice what is aching, well, there's something got in the air here. You see the source is moving in this direction. The wavefront is getting closer and closer to the wavefront, and when it does reach exactly that, the envelope of the wavefronts forms a cone with a half angle of sine theta is equal to V over Vs. Okay. So Vs is the speed of the sound, velocity of sound. V is the velocity of the aircraft. Okay. Whatever is beeping. And the sine is V over Vs. Now, they sure don't give a lot of if this is Vt and this is Vst, where Vs is velocity of the source, I think, that's where I'm having trouble seeing. No, I guess v is the velocity of the sound, the wave velocity. Vs is your source velocity, because they have the source being as one of the center. Okay, as this is speeding up and getting closer and closer, then if you look at this, there's your velocity of the source in this direction. Your velocity of the sound is certainly in all directions. Still trying to see how they get that sign relation. Oh, here's the angle theta here. Okay, got it. This is your hypotenuse. This is a right angle here. Okay, got it now, because this is your wavefront. This line here represents the parallel wavefront here. Okay, this has to be perpendicular to it. This is your VST. This is VT. So the ratio of VT to VST, that's this distance to that distance. That's a 90-degree angle. The ratio of this to that, the t is the same, so they fall out. So that's the ratio of v to vs. And if this is the hypotenuse, there's your 90 degrees. This angle here, that's the opposite over the hypotenuse, v to vs. So yeah, trying to figure out the drawing here. That is your, the envelope of the wavefront forms this cone with the half angle. That means just from the horizontal up here. Full angle would be twice that. Okay. It's not an easy picture to see. Circle represents the wavefronts emitted by the source. The tangent lines are drawn from Sn to the wavefront center to S0. Okay. Tangent lines are drawn from Sn to the wavefront center to S0, which is here, and it's also tangent to every one of those. Okay. The angle between one of those tangent lines and the direction of the wave is given by sine theta is equal to V over Vs. Theta is measured from the line of the source, path of the source. The ratio of Vs over V is called the Mach number. Gotta get some water in my throat. Really, boy. Velocity of source over velocity of the wave at whatever temperature that is. That's called the Mach number. When this is the same, you're at Mach 1. When you're twice the speed of this, you're at Mach 2, Mach 3, and all. The conical wavefront is the shock wave. Okay, that is the place where you're hitting. Now, this I think is one of the neatest pictures ever. Now, I've seen it from several sides. I'm sure several people have taken it. Now, what is happening there? You only see this on a relatively clear day. You've got some clouds in the sky, but not many. And what happens? Literally, those wavefronts, okay, 10 o'clock scholar, okay, good deal. I take it this is sound, right? Okay. I can't remember well, but how I remembered was you were the only Y chromosome present last time, so you had to be sound. There's one other that hasn't shown up, Kamari. Oh, I forgot to mark Shakina, it goes by Shakina. And all the rest are X chromosomes, okay? So here is, as this plane is going forward, is compressing the air molecules together, okay? Now what makes a cloud is when the water molecules, which are in the air, also get compressed. And if it's a relatively clear day with not that much moisture, but a little bit of moisture in the air, then these water molecules do get together, and the plane is approaching that thing, and when it emerges from it, it's broken the sound barrier. Okay, so really neat picture. I love that. The shock waves carry the energy concentrated on the surface of the cone with correspondingly greater pressure variations. The jet produces a shock wave that's seen as a fog of water vapor. So if it's a real cloudy day, you're probably not going to see it anyway because there's clouds all over the place. And if it's super, super dry, it just won't be much of a cloud. But on a fairly clear day with some clouds in the sky, yeah, you probably will see it. The large pressure variation in the shock wave condenses water vapor into droplets, and that's what you see there. Okay. Neat picture. Okay. Now we're moving to 14.7. Oh, here's another quick quiz. 14.3. As an airplane flying with constant velocity moves from a cold air mass into a warm air mass, does the Mach number increase, decrease, or remain the same? As an airplane flying with a constant velocity moves from a cold air mass into a warm air mass, does the Mach number increase, decrease, or remain the same?
Remain the same.
Okay, I hear remain the same. Well, V sub s is the velocity of the source. We just were told it remains the same. V is the velocity of sound in air. But remember, the velocity of sound in air does change with temperature. And how does it change with temperature? Okay, hold on to your pants because we're moving really fast here. Okay. Whoops, did I pass it? No. I'm not moving very fast down that at all. Okay. Ha! There it is. This is the velocity of sound in air at 0K. Not sorry, 273K, 0C. If T is greater, T increases from what you had, then the velocity goes up. If T goes below that, the velocity goes down. So velocity increases with increase in temperature. So, move back to the present. Here we go. So V, as you're moving from warm air mass to cold air mass, from cold air mass into a warm air mass, what is your V doing? It's going up, it's increasing. And if that's increasing, the Mach number is decreasing. Right? If your denominator increases, that stays the same. Your fractional value, your ratio decreases. So the Mach number actually decreases. So that looks like a B to me. Let's go to the back and see what we get there. 3B. Got it. All right. Now we go to interference of sound waves, 14.7. Sound waves can be made to interfere with each other, a phenomenon that can be demonstrated with a device shown in 14.5. I guess they're not going to show it. Okay, so you have to look in your book. Okay. Sound waves interfere. Constructive interference occurs when the path difference between two waves' motion is zero, or some integer multiple of the wavelengths. So the path difference, the difference between the paths, is some integral multiple of that wavelength. Destructive interference occurs when the path difference between the two waves' motion is an odd half wavelength. Okay? So in other words, this would be when the path difference is pi is 0, pi, 2 pi, 3 pi, 4 pi. It's destructive interference when it's 1/2 pi, 3/2 pi, 5/2 pi, 7/2 pi. That's when the path difference is of those values. Sorry about this. Let me back off. Lambda, I was saying pi, I don't know why I was thinking trig. This is 0, lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda. And destructive interference when that path difference is lambda over 2, 3 lambda over 2, 5 lambda over 2, 7 lambda over 2, all those values. Okay? Then you get destructive interference. Constructive when they're whole lambdas, destructive when they're odd half lambdas. Okay? Now, I wish they had this picture. Maybe they're going to come up later, but it doesn't look like it because now it's moving to standing waves, which is 14.8. So no, they're not going to show the picture. You'll have to look in your book. I wish they had it. A sound wave from a speaker S enters the tube and splits into two parts at point P. Okay? Yuck. This is going to be very tough for me to draw. The two waves combined on the opposite end are detected at the receiver R. That's your ear. If those two paths are exactly a whole number of lambdas apart, you have constructive interference and you actually hear well. If they're exactly an odd half wavelength apart, then you hardly hear anything at all. You have destructive interference. So that's what they're getting at, but without the picture, it's really hard to say. Okay? Or see. Now, before we move off of this, there's a tip 14.3. Do waves really interfere? In popular uses, to interfere means to come into conflict with or to intervene to affect an outcome. This differs from the use in physics where waves pass through each other and interfere but don't affect each other in any way. So in other words, they enhance or they detract. They really don't, in a sense, interfere because they don't. So their example 14.6 is there, and you're certainly welcome to solve it. I think it's a pretty straightforward problem, but if you need me to work it, just let me know. I'll be glad to try to work those. All right. Now we're ready for 14.8, if there are no questions. Standing waves. What in the world do we mean by standing wave? Okay. Here's a traveling wave. Let's just say it's doing that. What if it hits the end here and reflects back on itself? Okay? If a traveling wave reflects back on itself, it creates traveling waves in both directions at the same time. The wave and its reflections interfere according to the superposition principle, which I think they probably hit in an earlier chapter, but basically when a crest meets a crest, that's positive interference. When a crest meets a trough, you go to zero. When trough meets a trough, you have enhanced trough, okay? That's superposition. With exactly the right frequency, the wave will appear to stand still, and that's called a standing wave. And what that means is, if they're coming like this, and they happen to hit just like this, and every piece of them hits at the same time, the frequencies are just so they do that, then they just look like they're standing still. In reality, they're still moving this way, but they appear to stand still, and that's called a standing wave. Now, let's see if they can possibly get a figure here. Not yet, okay? A node occurs where the two traveling waves have the same magnitude of displacement, but displacement for an opposite direction, so that adds a zero. The net displacement is zero at that point, and if this one's always the same as this one, and they're adding, no matter whether they're here or here or here, it's always going to be zero. Even though the waves are moving, at that point, it's always zero. The distance between the two nodes is 1/2 of lambda. Okay, why 1/2 of lambda? Because one node is like this. I mean, here you have two nodes. One is like this and one is like this. That's a lambda. The distance between these two nodes is half lambda. The antinode occurs where the standing wave vibrates at the maximum amplitude. That could be up here or it could be down there. Those would be your antinodes. Okay. Here's a picture of this. Okay? And this is the picture 14.7 in your text. A large amplitude standing wave results when the blade, here's a vibrating blade going up and down like this, and here's a wall here that reflects on it. When the blade vibrates at a natural frequency of the string, meaning that this could just be one up and one down. That would be a natural frequency. Two up, two down. That would be a natural frequency. The one they showed here is 3 up and 3 down. Those are your natural frequencies. In other words, the distance between the source and the wall is exactly a fraction of a wavelength. That's a strange way to say it. Exactly in wavelengths, or in over 2 wavelengths, in fact. Okay. The nodes must occur at the ends of the string because these points are fixed, both here and here, and then however many nodes you have in between. These are what they call the antinodes. Those are the nodes. Antinode, node, antinode. Okay. That would be a natural frequency of the string, meaning that you have exactly so many wavelengths on there. And actually, exactly a half number of wavelengths on there. All right. Now, they talk here about the pink arrows. To me, they're red. I don't know where they get pink. The pink arrows indicate the direction of motion of the parts of the string. So here we have, I assume the source on this end and the fixed part on that end. Certainly that has to be a node. There's a node in the middle and a node there. Okay? Now, the pink or red arrows indicate the direction of the motion of parts of the string. Obviously, these are going down. This is fixed here. Okay? So they're going down here, up there. Okay? Now, at some point, that string is flat, but its still motion is down and motion up here. Because it was up here,
going down. It just has to be flat there, and going up. Okay? It continues that way until it stops right here. And this is where you're at time. Okay. The slide leaves a lot to be desired. Okay. This is little t time, this is counting time. T equals 0, that's how it is. At t is equal to the period over 8, 1/8 of a period. Now this is on its way down, on its way up. At 1/4 of a period is here, flat line, okay, but still moving in those directions. At t equal 3/8 of the period, then it's still moving down, but it's still moving up. But when t is equal to exactly the period over 2, no, it's exactly the opposite of that, meaning exactly 1/2 period has occurred. It's gone from that to this, and that time is t, your period over 2. All right. All points on the string oscillate together vertically with the same frequency, but different points have different amplitudes of motion. The frequencies are the same, but the amplitude, the amount of movement, are different. Obviously, the ones in the centers here are greater than the ones on either side, because the ones right here never move. There's always 0. Okay? Because it happens to be just at the right standing or characteristic frequency of that string. Sorry. Goodness gracious, I'm running out of energy fast. All right. The lowest frequency of vibration, which we're going to call B, is called the fundamental frequency, F1. Oh, that's a figure B. I was going to say, why are they calling it B and F1? As pictured in B. Now, here we have the setup. We have a fixed distance between this, that's L. The string is exactly L, it's exactly taut there. If you were to pluck this string, pull it up here to amplitude A and release it, then it sets up a perfect fundamental first harmonic frequency. Now, what has to be true about this? This length between this node and that node has to be exactly 1/2 of a wavelength, because it's only going in one direction. It comes down and does the second, that's the second half, okay? That's it. That's called the first harmonic. Higher harmonics are positive integer multiples of that first harmonic. Now the fundamental frequency, F1, then multiples of that, okay? Now when you multiply the frequency, you're having the wavelengths. Okay? This would be the maximum wavelength, fundamental wavelength. That would be twice the length between here. Here would be the second harmonic. Here you have one node in between, so you have one complete wavelength here. This was half of a wavelength here, meaning the wavelength was twice as long. Here the wavelength is exactly that, so it's half of what this one was. Okay? Second harmonic. The third harmonic is when you set up 1.5 waves here. One full wave plus half of another, so that would be 3/2 of a wavelength, would be that distance there. The frequency is exactly half of that frequency and 1/3 of this frequency. Okay? And this would be 2/3 like that. So your frequency of your first one, of the second one, would would be twice the frequency of the first, which would be n over 2L times the square root of alpha over mu. Where did that come from? Alpha is the tensile string, mu is the linear mass density. Now I'm trying to remember, did we hit those last time? I don't recall that we did. Okay? So where they're getting those values from, and this is the weird thing about the way Alabama splits up the physics courses. This is physics 2, and in physics 1 they did beginning of vibrations and waves, and in physics 2 they do sound. Okay, so if you went back to vibrations and waves, which was chapter 13, you would get those definitions. And unfortunately, though, that was the last thing covered in 201, and it's been a while, okay? And if you took it from a different source, you may have... why they split that up, I don't know, but they did. But that's what these stand for. Let's see if they even mention that here. I hope they do. Okay, alpha is the tension in the string, and mu is the mass per unit length, which is called linear mass density. So that's your formula for, and it's, I'm sorry, it's given at the bottom in 14.7, bottom of the page, 474, sorry about it. I may have to do a quick time out and go get some water. Okay, let's see if we can go. And this would be true for any harmonic. They only showed 3, but if you go on. We're assuming the tension is fixed and the linear mass density. Same string, so that should be the same. And we're assuming this tightness is the same. So this gives you the various fundamental frequencies of that. We've hit quick quiz 14.4 here. Let me see if I can finish 14.8, and then I will run and get some water because I've got to have something to help my throat. Let's see. Start at 5:30. Okay, let's do quick quiz 14.4. If you got your text, this is the bottom of page 474. Which of the following frequencies are higher harmonics of a string with a fundamental frequency of 150 hertz? So the fundamental frequency here is 150 hertz. Okay? Which of these would be higher harmonics of a string with that fundamental frequency? Okay? A, 200 hertz. B, 300 hertz. C, 400 hertz. And D, 500 hertz. E, 600 hertz. Okay? Of those 5, which, 1 or more, 0 or more, would be higher harmonics of the string with a fundamental frequency of 150 hertz?
B for sure. That would be the second harmonic. Any others? Second? E would be the? Which one? Fourth harmonic. You don't show the third harmonic, where would be the third harmonic? $450. They just don't list it. So B would be the second harmonic, and E would be the fourth harmonic. 450 would have been the third, but they just didn't list it. So let's see what they got. 14.4, B and E. Excellent. Okay. Now, I don't know if any of you are into this. Guitar fundamentals. See, are we there yet? Let's see. All right. No, we're not quite there yet. Let's finish the slides first, then we'll go to that. In fact, I guess we should have finished the slide before we got there. I didn't realize there was more here. F1, F2, F3 form a harmonic series. F1 is the fundamental, also first harmonic. F2 is the second harmonic, or the first overtone. Oh boy, they have to have so many different names for them. F3 would be the third harmonic or the second overtone, okay, and so on. Waves in the string that are not in the harmonic series are quickly damped out. They just get, in effect, when the string is disturbed, it selects its standing wave frequencies and then goes with it, okay? So those are the ones you get now. Yeah, that's still the stuff. We should have done that before we did the quick quiz. I just got ahead of myself. Okay. So here we have then guitar fundamentals, and you can look at that. It's pretty. I think they do a pretty good job of describing. And then they do harmonics of a stretched wire, and that uses that other formula, the one with the F and the mu in it, the tension and the linear mass density. And again, it follows pretty closely to what you see in the book. Again, if you want me to do any of these, please ask. I'll be glad to do them. All right. Now, force vibrations. Now my voice is cleared up. I'm not gurgling anymore. I guess I can go on. Okay. Force vibrations. A system with a driving force will cause vibrations at a frequency of that driving force. Okay. Are you understanding what driving forces are, or is that just a blah, blah, blah word? What's what? Yeah, that's what's making it move. When the frequency of the driving force equals the natural frequency of the system, which would be that string length, the system is said to be in resonance. Okay. So what if you have a driving force? In other words, something that's making the string vibrate. Okay. Whatever it is vibrate. Causes the vibration of the frequency of that driving force. When the frequency of the driving force happens to equal the natural frequency of the system, then you're said to be in resonance. Okay, not residence, but resonance. Okay. Now, I don't know when to give the example of this or not. Let's go on and see what they do, and then If I find a good place, I'll put it in. Pendulum A here is set in motion. Now it looks like pendulum A has a moderate length wire. It's set in motion. Okay? Pendulum B looks like it has a longer string, and D looks like it has a shorter string. Sure enough, C looks like it has about the same length of string. So if you have them all there, and you start moving A, okay, the others begin to vibrate due to vibrations in the flexible beam, because that beam does, that frequency of A does make the beam move a little bit, but they're not in the same. But pendulum C actually starts oscillating at the greatest amplitude, since its length, and therefore its natural frequency, matches that of A. Okay? So if pendulum A is set in oscillation, only pendulum C, with its length matching that of A, will eventually oscillate at a large amplitude, or in other words, resonate with A. Okay. That's at least an introduction to resonance. Okay? Let's see if we can go a little deeper with it. All right. Have you ever, with a kid, gone out and started pushing them in a swing? Sure you have, okay? Or you've seen it done once. And what you do, you wait till the swing reaches the maximum height, and then you give a push. Right when it's starting to go in this direction, you give it a push, and therefore you'll increase that swing. If you push too soon, it actually slows it down and messes it up, and the kid gets mad at you, right? If you wait too long and push, you're not going to have the same effect. But if you push at the natural resonance of that swing, then the kid gets to go higher and higher and either scream, stop, stop, if he's a bit like me, or higher, higher if they're really risk takers, okay? That's an example of that. Now, it's not just the child being pushed. I bet you some of you may have done this with a car before. I know I have. When a car is broken down and you need to get it out of the way, you can stand there and push to your heart's content. You're probably not going to move the car, no matter how hard you push. But if you push some and release and let the car roll a little and come back, and then just when it starts rolling again, push again and do like this, after a while, you can get the car rolling. If you push with the natural frequency of the car. Have you ever done that? Yeah. You get with the swing. If you just go and push as hard as you can, you're going to wear yourself out. But if you push and then push with it, and then you don't have to push that hard, just add to the natural frequency of the car, and soon you'll have it moving. And then you just keep pushing. Okay? Now, many years ago, I don't know if you ever saw it, it was Ella Fitzgerald would hit some high note singing, and the crystal glass would break. But they'd also do it using Memorex or something like that, a recording, and it was showing how perfectly pure the recording was. And the question was that really Ella, or was that Memorex? You know, I don't know if you remember the commercial, but it did. You can shatter glasses if you happen to hit exactly that frequency. Now, I don't know if you've ever had some of Mama's crystal, really fine crystal, wet your finger and go around the rim of it. Have you done that? Do it sometime, and keep doing until you hear it start squealing. When you hit that natural frequency, your rubbing is going to be that. And if you were to continue, you might wind up breaking her fine crystal, and then you'll be in deep trouble. So just get the nice loud noise. But you'll hear that, and you can tell when you're getting close to that frequency. Okay? Now, a really sad story. There was a bridge, and I can't remember if this was Washington State or Oregon, somewhere out there. I think maybe Oregon, but I don't remember. The Tacoma Narrows Bridge was built across this narrow, okay, connecting an island to the mainland or a peninsula to, connecting something, a pretty high major bridge. And I don't know if you've ever been on the West Coast, have you? Any of you? The wind always blowing, okay? San Francisco is just about as much as Chicago, the windy city. And I think Seattle and Portland and some of those are too. They're maybe a little more protected. But the wind is always blowing off the Pacific Ocean, fairly constant and pretty good, deal. It varies, of course. Well, they built this Tacoma Narrows Bridge, and they never thought about this because they didn't think it could ever happen. They happened to build the bridge fixed between 2 points at very close to the natural frequency of the wind out there. And literally, that wind came up pretty strong and happened to meet exactly the frequency of the bridge and started blowing on that bridge, and the bridge started rocking and rolling. There were actually cars on it, and it literally ripped itself apart. There are videos out there. See if you can find those. They're old, so they're black and white. The cars look old. It tore itself apart. After that, civil engineers, when they went to building bridges, they did everything they could to make different pieces of the bridge at different natural frequencies and get them as far from the normal prevailing wind. Now, the upper deck of the Nimitz Freeway collapsed due to the Loma Prieta earthquake. Now, I'm not familiar with that one, but what I'm thinking has happened is the earthquake sent forth seismic waves that just happened to match the Nimitz Freeway natural frequency and literally tore it apart. Okay? Even though the Loma Prieta earthquake was pretty far away, if I'm understanding that correctly. Now, this very weekend, last weekend, we were up on Smith Lake at a house that had a deck on it. And it was a fairly well-constructed deck, I'm sure. But one of the dogs that our friends brought, named Bean could never sit still. Bean was always pacing back and forth, and happened to pace at something pretty close to the natural frequency of that deck, because when Bean went by, you could feel the vibration. And Bean's a little dog; it couldn't be more than 35 pounds or so, but just happened to have a very regular gait and went at the frequency of that and resonated with the beat. Okay, Tia, right? All right, welcome. Okay. So, and actually, cats, when a cat walks, it walks at a very fixed frequency. And if it happens to be walking on something that has, that's a harmonic of that frequency, its natural frequency, a cat can get something. Something as light as a cat can get things rocking and rolling. Those are examples of resonance. Okay. Oh, here's a picture. On page 478, it says 1940, The turbulent winds set up a torsional vibrations in the Tacoma Narrows Bridge and literally and just the wind blew the bridge apart. So if you can get that, look at that in your book. You see it start moving a little bit in the A picture. Once established, the resonant condition led to the bridge collapse. I mean, it just rocked more and more and more. It's just like pushing the car. You get a little further each time, as long as you get on that resonant frequency, and it kept there, and it literally tore the bridge apart, broke it into, and unfortunately, I think there was a car on that section that made its way to the bottom. Don't remember if anyone was killed then, but it had to be very frightening. A number of scientists, however, have challenged the resonance interpretation. They don't think it really could have happened, but man, how else could you explain it? Okay, now we're moving to standing waves in air columns. Okay. So what we have here, if one end of an air column is closed, that makes it a node. A node must exist at that end, since the movement of air is restricted there. If the end that is open, the elements of the air have complete freedom of movement, then an antinode exists of maximum momentum, So, here is that situation. Well, wow. I sure jumped the rabbit here. Here's a pipe open at both ends. If it's open at both ends, that's got to be antinode at both ends. There's the first harmonic. They started off talking with a closed end. Now they're doing open end. Second harmonic then is an antinode, and one in between. Okay? Now in this case, the fundamental frequency goes from here to here. That's exactly twice the length of one more wave, one more time down here, exactly this over here. That would give you 2L, this length is L, that would be a wavelength. So with one node, two antinodes, that's half a wavelength. So the length of this is exactly half a wavelength. However, if you get another antinode here, notice you start at the bottom, top, bottom, so that's one complete wave, or top, bottom, top, that's one complete wave. Then that same length is your second harmonic, which is lambda 2. Okay? Your third harmonic, where you get two antinodes in between, so you get one complete wavelength and half of another. So this is 3/2. The L is 3/2 of your lambda. In other words, lambda is 2/3 of that length. There's one wavelength and half of another. So 1.5. So the frequency here is 3/2 your fundamental frequency that you have up here. 3 times half the wavelength. Okay. That's a pipe open at both ends. Okay. I just can't figure this. They started out one end closed and the other end open. And they talk about it, but they show no pictures. And neither they show them in the book. And then they go to showing the open on both ends, and then this now is talking about that one. A pipe open at both ends, natural frequency of vibration forms a series whose harmonics are equal to integral multiples of the fundamental frequency. Fundamental frequency would be where you have, that's half a wavelength, okay? In other words, F1 is V over 2L, okay? I'm sorry. This is the fundamental wavelength, and then multiples of this will be, where n is 1, 2, or 3. So that would be, when it's 1, it's V over L, that's one, exactly one wavelength, that's the second harmonic. Yeah, second harmonic, first overtone, okay? And then when it's 2, no, 1 would be 1 over 2, so that's 1. 2 would be 2 over 2, so that's exactly one wavelength. 3 would be 3 over 2, and that's what we saw here. 1 over 2, 2 over 2, which is 1 here, and 3 over 2 here, which would be 3.1. Okay. Now they did this for open at both ends. Open at one end, they just talk about it, but don't do a single thing with it. Okay? And I'm trying to see if they did any of the formulas in the book that way. They do give the formula, 14.19. Oh, here it is. I swear, this is so screwed up. Here they have one end closed and the other end open. No, I'm sorry. This is talking generically. If one end of an air column is closed, a node must exist there. If one end is open, the elements of the air have complete freedom, so that's an antinode. So if one end is closed, it's a node at that end. If one end is open, it's an antinode at that end. That's just preliminary. Then they start with the case, both ends open, so they're both antinodes, so that's what you get. Second, and then this is the summary of that, and that's what you get there. Okay, sorry. Then they do closed at one end. I thought that's where they were starting at the beginning, but they were just giving the basic background. So this one, you're closed at one end, so it has to be a node. Open at the other end, so it has to be an antinode. So your first frequency of this is 1/4. The wavelength is 4 times this, because that's just a quarter of a wave. The next quarter will get you back to the node. The next quarter gets you to another antinode, and then you get back here. So this, 4 times that length, is your first harmonic. Okay? They don't show a second harmonic because it doesn't have one. Okay? Because you see, the second harmonic would have been this, but it can't. It has to have an antinode here. So it's here. So what have you got? You've got one node. There's half a wavelength. There's 3/4 of a wavelength in that pipe. So 3/4 of a wavelength is that L. So the L is 4/3 of your 4/3 L is that next wave, and that's your third harmonic. They skip the second one. They can't have a second one. The second one would be where you had a node here, but since that's open end, you can't have a node there. So you have to wait till the next one. The next one would be 5. The 5th harmonic, or 4th overtone. This would be 2nd overtone. Okay? So that would be, so when you're closed at one end, you can only have odd number of harmonics. And then you have, there's one complete wave, and then 1/4 of another wave. So 5/4 of a wave is that length, so the wavelength is 4/5 of that length. Okay? And the 5th harmonic is 5 times the first one. Okay. Had me going there for a while. So here's the formula for that. The closed end must be a node, the open end must be an antinode, and then your frequencies that are allowed are only where ends 1, 3, and 5. Can't have a 2 and 4 because there's no even multiples of the fundamental harmonic, because the even harmonic would have closed at both ends, and then you don't have much of a pipe. Okay. Now, the next section is going to talk about beats. And we love beats. They're nice and red. No, I'm sorry. We'll get back to that in a minute. Let's look at quick quiz. A couple of quick quizzes here. A pipe open. Every time I see a pipe open, I want to say a pipe organ, because I think of that when it's a pipe open at both ends, resonates at a fundamental frequency F open. What a name. When one end is covered and the pipe is again made to resonate, the fundamental frequency is F closed. So the fundamental frequency with both ends open is F open, and the fundamental frequency with one end closed is F closed. Which of the following expressions describe, and by the way, these two pipes are the same length. Get that. Which of the following expressions describes how these two resonant frequencies compare? Okay? Okay. Find one that has some writing room. Okay, I think this probably has as much writing room as any of them. Okay. A. I'm going to write closed and open. I'm going to write C and O. Is this true? F sub C equal F sub O? Or B, is F C equal to 3/2 F open? Or C, is F closed equal to 2 F open? D, is F closed equal to 1/2 F open? Or E, none of the above. So since it's talking about above, that didn't say it, just said none of these. I just put above. I put it underneath for none of those above. Okay. Now, what we're looking at here, this one right here, happens to be F open. This is open at both ends. So this is an F open. And this is the fundamental, right? Fundamental frequency. That's an FO, this one here. So FO here is 1 D over 2L. Okay? So it would be D over 2L. Now we're assuming the velocity is the same and the length is the same. Okay? So F sub O, according to this, F sub O is equal to V over 2L. Let's go a couple slides. And here our F, okay, let me back up here. Yeah, I did it right. This is F sub C is equal to V over 4L. Okay? So let's go back here. F sub C is equal to V over 4L. Again, the velocity is the same, the L is the same, so what could you say about these two? You multiply this by 2, you get that. So this says that FO is equal to 2FC. Which is that? Whoops, we did it backwards. So that says FC is equal to 1/2 FO. Now that's what I see in this, so that would be D. Agree or not? Okay, let's see what they say. 14, that was 5. D it is. Okay. 14.6. Balboa Park in San Diego has an outdoor organ. When the air temperature increases, the fundamental frequency of one of the organ pipes, number A, increases. B, okay. I think I'm going to have to erase this. Yuck. There it goes. All right. Balboa Park in San Diego has an outdoor organ. When the air temperature increases, the fundamental frequency of one of the organ pipes, does it increase? B, decrease. C, stays the same. D, impossible to determine. Or E, no, I'm sorry, they don't have an E. Okay. The thermal expansion of the pipe is negligible. Okay, so don't worry about that part. Now, the temperature of the air increases. Going back to an earlier thing, which in this formula changes? Okay. L changes? No. They just said the pipe, opening, assume no change. D changes. The temperature increases, that increases. So what happens to the fundamental frequency? It has to be increasing as well. So we're going with A. Let's see what they went with. 6 is A. Perfect. Way to go, team. Now, that finishes the text here. They have an Applying Physics 14.3, Oscillation in the Harbor. Applying Physics 14.4, Why are instruments warmed up? 14.5, How do bugles work? 14.9, Example 14.9, Harmonics of a pipe. And 14.10, Resonance in a tube of variable length. Do you particularly want to see any of those work? If you do, just call it out. If not, we'll move on to beats. We love our beats. Make good borscht, right? Never mind. Okay. This is 14.11, beats. Beats are alterations in loudness due to interference. Okay, interference is all over the place here. The waves have slightly different frequencies, and the time between the constructive and destructive interference alternates. The beat frequency equals the difference in frequency between the two sources. Okay. This slide, you've got to read the book, I think, to figure out what they're talking about. Let's get a little background here. Interference phenomena we have been discussing so far have involved superposition of two or more waves with the same frequency traveling in opposite directions. Another type of interference effect results from the superposition of two waves with slightly different frequencies. Not two waves traveling in opposite directions at the same frequency, but two waves traveling with slightly different frequencies. So therefore, you have a frequency 2 and a frequency 1. Okay? So the beat frequency equals the difference between those frequencies between the two sources. So you have two sources, one with a frequency 1 and one with a frequency 2. The beat frequency is the absolute value of the difference between the, in other words, if frequency 1 was less than frequency 2, the beat frequency would still be a positive number. Absolute value ensures that. If 2 is greater than 1, then it's still going to be what it is. So the beat frequency equals the difference in frequency between the two sources, the absolute value of the difference. Okay. Now, here's the situation. Rather strange, but true. If you look here, we have a blue curve. The blue curve is like this, and if you'll notice, the blue curve starts out as a little bit longer wavelength than the green curve, meaning the green curve has a slightly higher frequency. As you see, it's inside blue here and on top of blue here. Kind of on top here, but inside here. So the green curve has a slightly larger frequency. But if they start off almost out of sync, almost the node here, but then right here they look like they're almost exactly out of sync, so they interfere, destructive interference, complete destructive interference there. And then they're just slightly out of phase here, so the green, the sum of these two is a little bit greater, and the sum, it's hard to say here, but you see they get a little bit more until somewhere down the line here, right here, or somewhere right in here, you have exactly constructive interference. They add exactly here. All along here they're getting closer, but here it's exactly the same. And then they start interfering with each other destructively again, so reduce until they get completely out of phase again here. It doesn't look like it's there, it looks like it'd be more there. But somewhere in there, you get back here again, and then they start increasing again until they're back in phase here. So you have this, and then back out of phase there, and then go back to here, they're out of phase completely. So that's a node again. Okay? Now, there wasn't a large difference between those, but the difference between those frequencies gives you your beat frequency, which would be that. That's frequency of 2, let's say in this case, we'll make that a higher frequency, that'll be the green one, minus the frequency of the blue one. Okay? Now, they're both fairly high frequency, but the difference between them is not a very large number, so that frequency is very small, you might say. So sure enough, the frequency here is much less than the frequencies of either of those. Okay. And that's all they do. That's the beats. Okay? that one formula there, okay, and that illustration of the formula, okay. If those two beats are really close together, really large numbers are pretty close together, then the difference is going to be pretty small, right? So the beat frequency is a very low frequency. Okay. Before we get to tuning forks, here's another quick quiz. Oh no, I'm sorry. Yeah, no, got it. You are tuning a guitar by comparing the sound of the string with that of the standard tuning fork. Pardon me? Okay, normally it would have started at, getting lost some time, 5:30 to 7:20. So we're already past 7:20, right? So it doesn't look like we're going to finish the chapter in time for lab today. So it's a lot like my last class. We're awfully close to the end, but it doesn't look like we're going to be there in time to do lab. So what we'll do next time, if we finish this chapter today, we're going to get started on chapter, what do we do next? It's chapter 15, electric forces and fields. We'll just get started on that, but next time we'll only go an hour and a half for class, not an hour and 50 minutes, and then have 2 hours for lab. And that way we will have, we'll get in a full 2-hour lab. See, most of the labs are set up to be 2 hours. But in the summer, because of the compressed time, they make 3 hours a week, but they split it into an hour and a half each, and it's really hard to get a 2-hour lab into an hour and a half. So what we'll do is next time have that. I'm guessing the next class we will have finished chapter 15, so we'll have another short class and then a 2-hour lab. And sometime or another, then we'll have to catch up and have a long class, and then, yeah. So we're going to do it. Our labs are basically 2 hours each. So we'll have, they won't always be every day. I mean,
So basically, it only be allowed for like every week,
no. Some weeks we'll have 2 and some we'll only have 1. But we'll always have a lab a week. Now this was weird because last class so much time was spent with the syllabus, the research paper, the whatever you call it, locator card, safety, and all those things. We didn't get much of a class in. Today we've gotten a full class, but if we had had the full class last time, we would have had time for a lab today. And so we'll just play it by ear, sound, okay, and do the, sorry, I'm not either, okay. When we finish a chapter, then the next day, if we have 2 hours left that day, we'll do the lab. If we don't, the next day we'll last the last 2 hours will be a lab. And if you finish in less than 2 hours, you get to go home early that night, okay? So we'll do that. Because the labs are really, in a regular term, they're 2-hour labs. So how can you change the labs in a summer term? You really can't. So what we'll do, we'll go on and continue on 14 until we reach the end. If we get into 15, we'll get into 15. And that way we'll be more likely to be ready for its lab on Wednesday of next week. So we have 14 lab on Monday. We may have 15 lab on Wednesday. If not, we'll definitely have it next Monday. And some weeks we'll have 2 labs, other weeks we'll only have 1. Okay. All right. I was trying to reach, that's beats. Quality of sound, okay. 1412 is quality of sound, the tuning fork. That's what threw me off, because 14.7, which is in this beats, is talking about a tuning fork, okay? But we already talked about a tuning fork earlier, so we're not doing quality of sound. But you are tuning a guitar by comparing the sound of a string with that of a standard tuning fork. You notice a beat frequency of 5 hertz when both sounds are present. As you tighten the guitar string, the beat frequency rises steadily to 8 hertz. To tune the string exactly to the tuning fork, you should A, continue to tighten. Okay, my writing stinks. B, loosen the string. Quit tightening and start loosening. And C, impossible to determine from the given information. Okay. Whoa! Which of those do you think it is? So let me go over the given again. You notice a beat frequency of 5 hertz when both sounds are present. As you tighten the guitar string, the beat frequency rises steadily to 8 hertz. Okay? It started off at 5. You tighten the string, and it went to 8. What's happening? What happens when you tighten the string? What happens to the frequency? It what? Decreases the frequency? No, it increases because, yeah, when you tighten, the pitch goes up, right? Are you a guitarist? Okay. So the beat goes up. So you've tightened it, and it's increased to 8. So what I assume here, this must be the tighten. This is the tuning fork, and that's the string. Because when you tighten it, the frequency went up, you've got a bigger difference here. So what do you think you have to do to get these to be the same? Loosen the string. To get this to go down to be the same, then the beats decrease until it goes to 0. Then you're on the way. Right? Does that make sense? So I think it's loosen the string, which I believe is, B. Let's see if I'm right. I'm guessing because I'm not a guitarist either. And I never could tune one when I tried. And 7, sure enough, is bravo in B. Okay. Make sense? All right. Example 1411, sour notes. That's what happens when I sing in church. Okay, never mind. Okay. If you want to do that problem, we can, or if you want to just work at it at home, I think it's pretty self-explanatory, but I'll be glad to do it. What you think? Keep going? Keep going, okay. So, quality of sound, 1412. And now we're talking about a tuning fork. Okay. Here's a little blurb over on the side. Tip 14.5. Pitch is not the same as frequency. Although pitch is related mostly, but not completely, to frequency, the two terms are not the same. I think I just used them as if they were, but they're not. The phrase such as the pitch in the sound is incorrect because pitch is not a physical property of sound. Frequency is the physical measurement of the number of oscillations per second. Pitch is a psychological reaction to sound that enables a human being to place the sound on a scale from high to low or from treble to bass. Frequency is the stimulus, pitch is the response. Okay, right. All right. So, tuning fork produces only the fundamental frequency. When you strike a tuning fork, you only get a fundamental frequency. Striking it harder doesn't make it go up in frequency or down, it just makes it go up in loudness, but you keep the same fundamental frequency. So, if this is your tuning fork, a basic frequency very well fits, okay? To me, this slide is a little on the wacko side, because this is an A and that's an A. What in the world are we talking about here? Relative intensity would be 1, okay? I guess I see. There's two figures in the book, figure 1427 and 1428, okay? This is the tuning fork, it's relative intensity, everything is the same. I mean, you've got one frequency, and it's all on that frequency, so that's why your relative intensity is 1. Okay, you have to look at the two figures together. They just don't show them together. The same note is played on a flute. This sounds a little bit differently, because a flute is closed at this end, if I'm not mistaken, open at that end. Okay, and then you're figuring with your fingers, and you happen to hit the same note of that. It's a little different. Same note played on a flute sounds differently because you have a first harmonic, which is what the tuning fork does, but on the flute, for some reason, the second harmonic is your strongest. Okay? So that messes with your frequency. You also have a strong fourth, which is almost as strong as your fundamental. Your odds go down, and actually the even here goes down too. So you have a mixture of harmonics. And that's what gives a flute the sound that it has. You just don't have a pure note, you have texture in the note, you might say. Okay? So the same note played on the flute, the second harmonic is very strong, the fourth harmonic is almost as strong or close to the same strength as the first harmonic, and the others get weaker the higher you go. Okay? The fourth is being a good deal stronger than third. So first, second, third, fourth, after that, always steadily. Okay? So that distorts that. So therefore, it's not exactly the same. The frequency seems to be very close, but the harmonics that come into play, they change it somewhat. Okay? Now let's do something else. Here is a clarinet. A clarinet is a reed instrument, and I guess it's sort of like it's open on both ends, kind of. I don't know. Maybe this end is considered closed too. On the clarinet, look at where your strength is. Way up here at the fifth harmonic. Stronger than the first, the fundamental frequency, but nothing else is as strong. The fourth is the third strongest, and the sixth is the third is fourth strongest, sixth is next, then second, then seventh. So you got a sort of a weird mixture there. So that throws things off a little bit. Same note, so same basic frequency, but you have a lot more texture or differences in that than you do in either the tuning fork for sure, because that's the one solid fundamental frequency. And here you have all the harmonics. Lots of harmonics contribute. The first and fourth harmonics are very similar. I would say that. They're fairly similar. With the third being close to them, but the fifth is so very strong. The third's close to them, the sixth is not too far behind either. But so yeah, you just have a lot of mixture there. Okay, so it changes the, I don't know if the right word is timbre or something. Okay. Yeah, that's it. In music, the characteristic sound of any instrument is referred to as the quality or timbre of the sound. Quality depends on the mixture of harmonics in the sound. We say that the note C on the flute differs in quality from the same note C on the clarinet. Instruments such as the bugle, the trumpet, violin, tuba are rich in harmonics. A musician playing a wind instrument can emphasize one or another of these harmonics by changing the configuration of the lips, thereby playing different music. Probably a bit more than I really care to know, but it's interesting. Applying Physics 14.6. Why does the professor sound like Donald Duck? Okay, you better not answer that question. No. Okay. Anyway, actually, what this is doing, and I bet you some of you have done it, most likely Sam, but maybe some of the rest of you. Have you ever been around helium? Okay, you've done it, haven't you? Okay, did you do it too? Okay, a helium balloon, let it out and breathe some of that. What happens? You sound like Donald Duck. Your frequency changes big time. That's what that one's about. Do you want to hear it or want to just read it later? It's pretty short. Yay or nay?
Yay.
Say again?
Yay.
Yay, let's do it. Okay. A professor performs a demonstration in which he breathes helium and then speaks with a comical voice. One student explains the velocity of sound in helium is higher than that in air, so the fundamental frequency of the standing wave in the mouth is increased. What you think? Yay or nay? It's really bogus. Okay. He's not keeping the helium in his mouth. That's not quite it. Another student says, no, the fundamental frequency is determined by the vocal folds and cannot be changed. Only the quality of the voice has changed. Which student is correct? The fundamental frequency has changed or the quality has changed? Neither? Explanation. The second student is the one that's correct. The fundamental frequency of the complex tone from the voice is determined by the vibration of the vocal folds in your larynx, okay, and is not changed by substituting a different gas in the mouth. That's not it. The introduction of helium into the mouth results in harmonics of higher frequency being excited more than the normal voice, but the fundamental frequency of the voice is the same, only the quality has changed. You went to different distribution of harmonics. That's what happened. The unusual inclusion of the higher frequency harmonics results in a common description of this effect as high-pitched voice, but that is incorrect. It's really a quacky timbre. Strange. I'm not sure that the description is all that clear, but what I think it's saying, it affects the folds of the larynx, so they give off different things. The helium interacts differently there. I'd always heard that. And here is the definition. Timbre. In music, the characteristic sound of any instrument is referred to as the quality of sound or the timbre of the sound. The quality depends on the mixture of the harmonics in the sound, as we just saw in the flute and clarinet, as opposed to the tuning fork. Pitch is mainly, though not all completely, is related mainly, though not completely, to the frequency of the sound. This is what my tip said at the beginning. Pitch is not a physical property of the sound. Frequency is the stimulus, and pitch is the response. It's a psychological reaction that allows humans to place the sound on a scale. Okay? In other words, some people have very close to perfect pitch. They hear something and can reproduce it almost exactly. Okay? A lot of that, there's several things going on there. What your ear does, that's what you receive. What your larynx does, that's what you put out. You may think you're sounding just like what you heard, but you see, your voice, what you hear is mostly the vibrations in the bones, not the vibrations that come here, because these vibrations are going away from you. You're hearing this. What it takes is that your bone structure produces very similar to what you project out. And that's not something that can be taught. It's something that you have. It can then be trained, but it's not quite the same. Now, 1413. Now, if this is getting too biological, we can skip it. But I think it is at least interesting. The ear consists of basically, I think they count it either 2 or 3 parts. I think it's 3. The outer ear consists of the ear canal, that's this part here, that terminates at the eardrum. There's the eardrum, which is a membrane, also called the tympanum. Yes, is how you pronounce that. Now, the outer part of the ear is just the fleshy part here that sort of catches the sound and directs it into the ear canal. So those are together, but really when they say outer ear, that's what they mean, not this part. Just behind the eardrum is what we call the middle ear. Okay. Now what the eardrum does, it vibrates on the sound that comes into the ear canal, and it hits the hammer, and the hammer hits the anvil, and the anvil messes with the stirrup. That's the middle ear. Okay, just behind the eardrum is the middle ear. The bones in the middle ear transmit the sound to the inner ear. These bones around here and in here, they transmit the sound to the inner ear. Outer ear, middle ear, inner ear. Okay. The bones in the middle ear transmit sounds to the inner ear. Okay. Down here, this bottom curve here, they're sort of jumping a rabbit here. There seems to be a big disconnect here between the previous slide and this slide. Bottom curve is the threshold of hearing. That's the faintest sound that we can hear. And it varies with frequency. Very low frequency, that faintest sound is pretty high intensity before we can hear it. As you go up in frequency, the faintest sound you can hear is much lower intensity. In fact, it gets quite low down here, around 4,000 hertz. That doesn't make any sense. It's less than zero intensity. That's not making a lot of sense to me, but it does make sense this gets quite low here. Okay. Then, as you go up in intensity, you're hearing better and more clearly, but it still varies with frequency. And it gets up here and things begin sort of to level off until somewhere up here, around 120 decibels, you're in pain. So here's the threshold of hearing, the softest, the lightest sounds you can hear, least intense, and this is where you start having pain and, frankly, damage. Okay? The threshold of hearing is strongly dependent on frequency, very strongly dependent on frequency. The easiest frequency to hear is about 3,300 hertz, somewhere in here. There's 1,533, somewhere in here is your easiest sound to hear. Very, very low decibel, you can still hear it. when the sound is loud, the top curve, the threshold of pain, all the frequencies can be heard close to equally well. Certainly in here, I think this is even closer, but here it is, but all the sounds are about, the frequencies are fairly close to equally well. Here, the difference in frequencies have a big difference in the threshold. Okay. That's all, folks, of chapter 14. Now, oh, wait. I didn't know we had comedians in here. Okay. I'm going to pause just a minute here. I've got to, huh? Yeah, for sure. Why don't you take one? I've got to, get new slides and stuff. I also want to find and see if I have the first test ready. I can't remember if I do or not. Goodness gracious, I think my papers have gotten all out of order. All right, I'm getting closer. Okay. Okay, I found my 214 test, but I haven't found my 202 test. Here we go. I think I have found it. These things have gotten way out of order. Yeah. Yep, I don't have it ready. I didn't think I did, but I just wanted to check and make sure. Okay, I have a test ready, but I can't recall if it's from this text or not. So I'm going to have to check on this before I want to give it to you. In fact, I have two tests ready. This could be it. But I still have to check, so I won't mess with it tonight. I'll try to have this ready for you when we do the lab on Monday. I'll try to have the test ready for you. And for some reason,
How many tests is it in all?
what's that?
How many tests is it in all?
I don't know. It's just depends on how many chapters we get to cover. If you remember at the beginning, I gave you several and said we might have time for this one, might not, so we'll see. We're off to sort of a slow start because, man, my computer is so, okay. just closed this and it's still open. I swear. My computer, okay, that's what I got here. Okay. I tried to go back to it, it wouldn't do, so I have to start over at the beginning. Here we go again.
I thought you needed to get some water.
What's that?
Don't you need to get some
I am. I'm just trying to get this set up before I go. I swear, this thing is so slow. I know what I need to do. First, I'm going to pause Screencast-O-Matic. I didn't need to do that. This thing is driving me nuts. Okay. Because I know you have a weekend to work on them, let me just talk about how the book is configured. At the end of the chapter, which we just finished, here's a summary. And there's not much of a summary from 14.1, that's a sort of introduction, but in 14.2, a few definitions, 14.3, a few formulas with definitions, 14.4, a few more formulas, 14.5, one more, 14.6, Doppler effect, another formula with a definition or two. Interference, talked about in 14.7, a couple formulas there. Standing waves, 14.8, formula there. 14.9, definitions, 14.10, definition with a couple formulas, and then 14.11 is the last they give a definition with a very simple little formula. Then there's conceptual questions. Now these conceptual questions, they have the odd number answers in the back of the book. Okay? Yeah. Maybe not all, but most of them do. But then the problems. Okay? The questions you're going to see on your test, which I hope to have ready for you Monday, will be similar to these problems in your book. 14.1 and 2 don't have any, or 14.2 is combined with 14.3, so any of the odds 1 through 9 there would be good, because the problems also have odd answers in the back. And then 14.4 and 14.5 together, they have questions 11 odd questions 11 through 23, quite a few of those. 14.6, the Doppler effect, odd questions 25 through 35. And then 14.7, interference of sound waves, odd numbers 37 through 41. And 14.8, standing waves, odd numbers 43 through 51. Force vibrations and resonance, only one odd number question, that's 53. Standing waves in air columns, odds 55 through 59. And 14.11, beats 61 through 67. 14.13, only one question there, 69. Only one odd question there. Then they have some additional problems that sort of combine things from several sections. Those are sort of section dependent. These are any of the odds 71 through 81. But again, you don't have to do these, but it's things that'll help you do well on the test and minimize the pain. Okay? I just realized that I should have known this before. That was the last I need of this diskette, because only the last chapter from part 1 was in this chapter. After this, we go to volume 2, of college physics, and that begins chapter 15. So where we're starting now, sorry we've got to start all this over again. Sorry about this. Did all that fiddling around with it trying to get it to work, and then now realize, okay, I think I can open it now. We'll see. Yes, there it is. And we'll be on this diskette from now on, so I won't have to be swapping. Okay, resources by chapter, 15, electric forces and fields, PowerPoint lectures. Actually, this seems, I shouldn't speak too soon, but it seems to be going faster than the other one did. I spoke again. No, here it goes. Here's PowerPoint again. This is so much fun. Starting. Loading. Processing. Opening. 0%. Or you're going to sit here for a while. Validating, opening again. Now it's moving 23, 29. Hanging up there again. Boy, this is pathetic. I hate Microsoft products. What's that? Not quite 14. 13. Huh? Ah, here we go. Hey, I got my salad eaten, and I got a sandwich eaten. I didn't get any fruit yet, but I'll eat that on the way home. Okay, I'll eat something else when I get home. Okay. We're into the main part of Physics 202, and that is electricity and magnetism. And we're starting with chapter 15, electric forces and electric fields. Okay? Now, the very earliest studies of these were made by the Greeks, who observed that electric and magnetic phenomenon as early as 700 BC. Okay? Did they understand it? No. Did we understand it? A little better, but not quite so well yet. And here's what they found. Do you know what amber is?
Yeah.
What? Okay, it's not quite a metal, but it's a solid.
Well, yeah, it's not.
And it's
It's like brown.
yellowish or brownish in color. It's naturally occurring, and what it is fossilized, petrified rosin. I don't know if it's pine rosin or some type of rosin. And anyway, they found that when they rubbed this amber, especially with fur, I believe it was, animal fur, it became electrified and attracted pieces of straw or feathers or other lightweight things, little scraps of paper, that kind of stuff. Also, they found they could take it and touch somebody at a party and shock them. And that was all lots of fun, right? Also discovered magnetic forces by observing magnetite. Anyone know what magnetite is? Naturally occurring magnetic rock, also called lodestone is the common name for it. What's that? Okay. And it attracts other magnetic materials. In other words, anything that contains iron, but not only iron. We'll talk about a little bit more of this later. But the Greeks discovered both of these completely separately and didn't think they had anything to do with each other. In fact, it was a long time before anyone realized they did. And actually one of the early scientists, and you don't usually think of him as a scientist, is good old Benjamin Franklin. Now, this is much later than the Greeks, 1706 and 1790. And by the way, he's a potential paper topic. Okay, hint, hint. I got my first paper in the last class, by the way. Already got a paper in. He was a printer, an author, a founding father of our country, an inventor, a diplomat, a scientist, a physical scientist. In the 1740s, he did work on electricity, and it changed the unrelated observations into coherent science. He was a pretty big cog in the wheel of scientists that contributed to our understanding of electricity. In fact, I think he's the one that we blame for, he just said arbitrarily, let's just name electrons negative. Therefore, protons positive. And unfortunately, that sort of messes up the way we look at things, but we'll live with it. Okay? So this is section 15.1, and the little blurb here in your text on Benjamin Franklin. They don't have this picture, but they have the blurb. Now remember, your book is not a source if you choose to write on them, but it can give you the idea. Okay. So, what are some of the basic properties of electric charges? Two types of charges exist. Okay? Positive charges, negative charges. Again, they were named and picked up by Benjamin Franklin. Okay? Now, it really doesn't matter too much whether it's a positive charge or a negative charge. What really matters is what your other charge is. If you have a positive charge here and a positive charge here, guess what they do when you try to pull them together? Huh? They repel each other. Well, then what would a negative charge and a negative charge do? They repel each other too. A positive charge and negative charge attract. A negative charge and positive charge, they attract. So it really isn't as important what the charges are, whether they're positive or negative, but whether they're alike or not. Okay? Like charges repel, unlike charges attract one another. I have too many stations here, it looks like. Nature's basic carrier of a positive charge is the proton. Now that's true. Okay? And meaning, when they say carrier, possessor is what I would say. Nature's basic possessor of a positive charge is the proton. Now, why do I not like the word carrier? In general, protons don't move. They're in nuclei. They don't move around. They possess the charge, but they don't move. The carrier of charge is typically the electron. Okay? And if electrons have fled the scene, then you're left with a net positive charge. If they excess electrons, then you have a net negative charge. So I say the carrier is the electron, but not a positive charge, a negative charge. Protons do not move. That's why I don't like the term carrier from one material to another, because they're held firmly in the nucleus. If you move protons, you've got nuclear reactions going on. We don't want that to happen. We don't move protons, we move electrons, which are negative charge. So that's why I have a problem with the word carrier. I would say possessor rather than carrier.
So what happens if you move a proton?
What's that?
What happens if you move a proton?
You move the whole nucleus. I mean, you don't move them. They're in a very dense nucleus. The electrons are what move. Okay. The only way to move a proton is to blow up the nucleus. In other words, a nuclear reaction. And let's not do that. Not in this class. Okay. Again, nature's basic carrier, I'll agree with carrier here, or possessor of negative charge, is the electron. And what you do when you charge things, you either give it excess electrons or they gain electrons, making it negatively charged, or they lose electrons, because electrons are the things that move, and then they become positive charge. Gaining or losing electrons is how an object becomes charged either negatively or positively. Now, electric charge is always conserved. You can't create charge, you can't destroy charge. You can just move charge around, exchange charge. And you do that through the electrons. Objects becomes charged when negative charge is transferred from one object to another. So let's say we have a neutral object here, and maybe another neutral object here. They have balanced charges, same number of positive and negatives, okay? How you get them to be unlike charges is move negative charges from this one to that one, making this negative and that positive. You haven't moved a proton at all. You only move the electron. Or you move electrons from here to here, making this negative and that positive. That's how you things become charged, because the negative charge is transferred from one object to another. You can't create charge, you can't destroy charge. You can neutralize charge by letting electrons move back so they can balance the charge again. Charge is quantized. Now, what do we mean by that? Charge is not a continuum. You can't have a certain charge and then less charge, and you keep going less charge and less charge, dividing by half or half or half or half, and go on forever. Can't do it. There is some minimum charge that's as low as you can go. All charge is a multiple of the fundamental unit of charge, and that fundamental unit of charge is symbolized by E. Now, in math, E stands for the exponential function. It's not the E we're talking about here. In fact, when I refer to an electron charge, I like to call it, let me get my pen activated again. I like to call it E minus. That tells me I'm talking about electron, not an exponential function or something like that. An electron charge is always negative. Now, there are some exceptions, and these are things called quarks. Now, I don't understand quarks. They are the things that make up protons and neutrons, not electrons. Only things that make up protons and neutrons. And quarks, physicists are strange. They name them up quarks and down quarks, top quarks and bottom quarks.
Is that like quantum physics?
This part certainly is. That's where the quantum comes from. And quarks probably came out of our understanding of quantum physics. I don't know exactly where they came from. And quarks are made up of fractional portions of charges. Like an up quark, I think, is a plus 2/3 charge, and a down quark is minus 1/3 charge. So 2 ups and a down would give you a positive 1 charge. That's what makes a proton. And an up and 2 downs, that's what makes a neutron, because then you have plus 2/3 and minus 2/3, no charge. So they're really strange. That's the exception. But all charge that exists in our understanding of nature, not within protons and neutrons, but in our understanding, are multiples of this electron charge. Electrons have a charge of minus E, and protons have a charge of positive E. How they get those is different. The SI unit for charge at System International is the Coulomb. Now, in this case, they capitalize Coulomb. Most of the time, they write a lowercase, but capitalize the unit, C. Why do they capitalize the unit?
Because it's somebody's name.
Name, exactly. I think his first name was Charles. Charles Coulomb, I think, was a French physicist. And the French really did a lot of the early work in electricity. It was about the time of Louis XIV, when France was really the premier country in Europe. they really spent a lot of time on arts and sciences and things like this, and Coulomb was part of that number. Ampere was another one, Andre Ampere. Okay? And guess who was an ambassador to France? Benjamin Franklin, you got it. He wasn't the only one. I think Thomas Jefferson was later or before, sometime or another. But I think Coulomb, I wouldn't be at all surprised if Franklin didn't get together with some of these French, if not these particular ones, either people who came before or after them. And that's where they exchanged a lot of ideas, I bet. I don't know that for a fact, but that's my guess. Now, what is that? The SI unit of charge is the Coulomb. The electron charge, E, is 1.6 times 10 to the minus 19 coulombs. That's a tiny, tiny fraction of this. You see, this is a macroscopic measure, something we can measure on an instrument or something. This is something that's way too small for us to ever measure, so that's why we don't use that. But that's the smallest quantity of charge, that's why they say it's quantized, that you can have on any object. And you can change it by multiples of this. So it takes an awful lot of these, about 10 to the 19 of these, to make 1 coulomb. Okay. All right, that covered pretty much what we call 15.1.1. Okay, let's move on to 15.1.2 and talk about conductors, but at the same time, we'll be talking about insulators as well. Let's start with conductors. Conductors are materials in which the electric charges are free to move in response to an electric force, which later we'll also talk about electric fields. Okay? So in other words, conductors are things that the charges can move pretty easily. Okay? Most of the time, that will be your metals. The very best conductor is actually silver. So why don't we wire our houses with silver? It's a better conductor than copper. Way too expensive. Okay? That's the number one reason. But there are actually other reasons too. Silver is a pretty brittle metal where copper bends easily. And you want your wires to be able to bend, go across the floor and that kind of stuff. But this is the best, and copper isn't far behind. They're so close. Aluminum, quite a bit further behind, but it's a very good conductor too. It's usually number 3 in most lists. Now, I don't know if you know what copper is often used for besides electrical wiring. Anyone know? Copper, when it's mixed with, I believe it's zinc, produces brass, I think. Maybe some other things in there. And copper, when it mixed with something else, or maybe it's zinc, produces bronze. And copper is mixed with several things that are used to make various alloys that have certain properties. Brass in particular is a pretty important thing because I believe brass does not arc and spark. Let me just say it that way. There's something about brass that makes it a pretty important thing. And what is brass used for a lot?
Instruments.
Say again?
Instruments.
What kind of instruments? Is it musical?
Yes.
Okay, possibly. And also things that you don't want to change a lot over time, like with heat, temperature, that kind of stuff. It has some pretty important properties that way. And some of the things that are pretty important that way, shell casings are quite often brass. Shell casings as in for guns, bullets, projectiles, things like that. Back in World War II, we were making an awful lot of bullets, an awful lot of bombs, an awful lot of projectiles, an awful lot of missiles, and things like this. So we were using copper for the war effort. So there was not as much copper available for people to wire their homes. So the agencies that controlled these things allowed houses to be wired with aluminum. It was not as good a conductor as copper, but it was the next best. Not as good as silver, of course. Silver was way too expensive. Aluminum was relatively cheap. So they allowed people to start wiring their homes with aluminum. Do you see many of these homes around anymore? This is World War II vintage. We happen to live in a house that was built in 1930, and our whole neighborhood, there's a lot of houses built in the 20s and 30s, but you don't see many that were built in World War II. I wonder why.
Because they use all the copper for weapons.
They what?
They use all the copper for weapons.
Okay, yeah. Well, why don't you see those houses anymore?
They
Burned down.
They burned down, exactly, because they weren't as good a conductor as copper, and when you tried to load them up, especially in the post-war times, and people started getting more and more electrical appliances, that aluminum would overheat, melt the insulation, catch things on fire, and those houses burned down. Or else they converted them from aluminum back to copper once copper got plentiful again. So aluminum did not make great wiring, okay, because it was the worst conductor and heated up worse. And a lot of those houses burned down. When a conductor is charged in a small region, the charge readily distributes throughout the entire surface of material. So if you were to put a charge on a copper wire here, you put it on and immediately that charge distributes across the whole wire, all throughout the wire. But it's only on the surface. It doesn't go to the interior of the wire, it hangs around on the surface. And then if you create a potential difference, we'll talk about that later, the charge is free to move. That's what makes it a good conductor. Okay. On the other hand, things that do not conduct well are good insulators. Insulators are materials in which the electric charges do not move freely. Some of the pretty good insulators are glass, rubber. A lot of the insulation, the coating of wires is rubber or some type of material like rubber so that you don't get shocked when you feel it, okay? You don't conduct across the insulator, okay? Thank you very much. Okay, those are types of insulators. Included in this, the glass would be things like porcelain. Have you ever seen on the power poles what they hold the wires off the wood or the metal or other things? Either glass or porcelain insulators, so it keeps the wires apart and they don't conduct through that. When insulators are charged by rubbing, like that amber with the fur, only the rubbed area becomes charged. It does not distribute across the whole material. So if you had an amber rod here, or a rubber rod here, or a glass rod here, and you touch a charge to it, the charge stays right there. It doesn't distribute like it did in copper, because copper is a conductor, glass, rubber, amber, those are insulators. Okay? There is no tendency for the charge to move into other regions of the material because the charge doesn't move easily. You put it there, it sits there. It stays there. Okay? It doesn't distribute throughout the material. Okay. If that wasn't enough that we had conductors or insulators, which are not conductors, we also have, and this came about much later, we discovered we had semiconductors. When you hear semiconductors, what do you think? Say again?
Not
Kind of.
really.
Is that what you said? Okay. Well, Okay, the characteristics of semiconductors are between those of insulators and conductors. Silicon, germanium are examples of semiconductors. And if you have a book, and I don't think many of you do, when you go to the back of your book, to your periodic table, even though this is physics, chemistry and physics are greatly related, here is silicon right there, and just below that is germanium. So they're right here together. They sort of conduct and sort of insulate. They're in between the properties. And given a certain situation, it will conduct and conduct pretty nicely. Otherwise, it doesn't. And again, where and how are these used? Computer chips. They use that characteristic of conducting in some circumstances and not in others. That's what makes chips and transistors and other things operate the way they do. Semiconductors. And Silicon Valley, the home of semiconductors. Silicon, that's where it got its name. Computer chips. Okay. When we're talking about creating a charge on something, we can do that several ways. We already talked about rubbing amber with fur. That's one way to do it. But another way is by conduction. So let's say we have a charged object, say this rod here. This rod may be that amber that we rubbed with fur, okay? And it's placed in contact with another object, say the sphere, okay? Now, before you actually touch it, okay? Let's say this rod has a net negative charge. You charged it up, rubbed that fur on it really, really hard, and got a lot of excess electrons on the surface of that rod, okay? So it's negatively charged. Let's take it close to that sphere. Now this sphere is a metal sphere, which means charges move easily, right? On the insulator, the amber, they just sit there on the surface. On the metal ball, the sphere, they move. You bring this negatively charged rod close to the ball, but don't touch. Then, because like charges repel, the negative charges, the excess electrons get as far away from this as they can. They get on the back side of that sphere. The leaving positive charges are collections of atoms who've lost their electrons. The electrons went over here, so the positive charge is here, which would really set up a bipolar situation or dipole situation. Okay? Now, if you go on and touch the negatively charged rod to the sphere, which is attracted to positive charges this side, touch, then these negative charges tend to neutralize those positive charges. But when they do that, that makes the whole sphere really negative, because these positive sites took away from this rod the negative charge and neutralized them. That left this negative, still a little negative charge there. After contact, the electrons from the rod flow into the sphere, neutralizing those local positive charges, leaving both of these slightly negative. When the rod is removed, negative charge remains on the sphere, but a little remains on the rod. Not as much as we had before, and this is as badly negative as this was before, but now, because you remove the rod, now the negative charges reassociate all over the sphere. Okay? So once they touch, some of the electrons from the rod move to the sphere, making the sphere slightly negative, making the rod less negative, but still slightly negative. When the rod is removed, the sphere is left with a net negative charge, and the rod has a less lesser negative charge, but still has something. The object being charged is always left with a charge having the same sign as the object doing the charging. Okay. Same thing would have worked if this was positive here. How you get a positive rod is, I think you rub silk on glass. Then the silk will take the electrons from the glass, leaving a positive charge. And then when you hold it near a metal sphere, the negative electrons flow this way, the positive goes that way. You touch, the positives distribute, canceling out these negatives, leaving this net positive and positive. Okay. So it works with either one. The object being charged always has the same charge as the charging object had. Okay. Now, that was by conduction. Here we're going to charge by induction. What in the world do we mean by that? When an object is connected to a conducting wire or a pipe buried in the earth, it is said to be grounded. So when an object is connected to a conducting wire or a pipe buried in the ground, it says to be a conducting pipe, it's said to be grounded. A neutral sphere has equal number of electrons or protons. Anything that's neutral has equal electron and protons. Doesn't mean it doesn't have any charges, but it has equal number of each. So the neutral sphere has equal numbers of positive and negative charges. So that's our first situation. All right. Now here's what we're going to do. A negatively charged rod, maybe amber that's been rubbed with wool or something like that, negatively charged rubber rod is brought near the uncharged sphere, the neutral sphere. Well, what does this negative charge do? Just like before, it attracts the positives here, repels the negative. So the electrons redistribute themselves because the sphere is conducting and the charges are free to move, and they redistribute when the charge rod is brought close. Charges in the sphere are redistributed. Some of the electrons in the sphere are repelled from the electrons in the rod and moved to the opposite end. A lot like we saw before. But this time, we're charging by induction. We're not going to let them touch. That would be conduction. The region of the sphere nearest the negatively charged rod has excess of positive charge because of the migration. The negatives went that way. So what if you let this reach ground? In other words, connect this to something that's grounded. Well, then what's happened? The electrons here start fleeing because you have net negative charge here. So that leaves this net positively charged. You haven't touched it. You just move them away. You let that be grounded. They flee because there's excess negatives there. And then you take off the ground and remove the rod, and then the conducting wires connected to the sphere allow some of the electrons to move from the sphere to the ground. Then you remove the ground, remove the rod, and what do you have? This is still as negative as it had before. The charges couldn't move anywhere, nothing touched, but you have excess positives here. So the excess positive charge would be non-uniformly distributed. As long as that thing is close, okay? All you did was remove the grounding wire. The wire to ground is removed, the sphere is left with excess induced positive charge because the positives were attracted this way, the negatives went to ground. You remove the ground, so you're net positive here. Okay. Because this rod is still close, they're not evenly distributed. Initially, the positive charge on the sphere is non-uniformly distributed, but what you do, you move this. Now let's see if they showed that. Yes. Eventually, the excess positive charge becomes evenly distributed due to repulsion between the positive charges. So remove the negative. Now they redistribute as evenly as they can. Charging by induction requires no contact with the object inducing the charge. It just requires an escape route to ground. Okay? The remaining electrons redistribute uniformly. The positive charges distribute fairly uniformly. There is a net uniform distribution of positive charge on the sphere surface. That's where the charges always go on the conduction surface. On a conductor, they go to the surface. Okay? So, charging by conduction leaves the same charge on the sphere as what you had on the charger. Induction, where they never actually touch, and you let the charges bleed away, that gives you the opposite charge from what was on the charger, you might say. All right. All right. Let's see if we can get polarization in here, and I think this will be the last slide. In most neutral atoms or molecules, the center of the positive charge coincides with the center of the negative charge. So if you think back to what we had before, atoms and molecules, okay, most of the time the electrons distribute evenly among this, the positive nuclei are evenly distributed, so everything is pretty balanced. But if you bring that into the presence of a charged object, then the centers may separate slightly. Because if you bring a negative near that, the positives are going to migrate this way, the negatives migrate that way. Bring a positive near that, the negatives migrate this way, the positives migrate the other way. Okay? That results in more positive charge on one side of the molecule than on the other side. And likewise, more negative on the other side and less on the positive on the one side. That realignment of charge on the surface of an insulator is known as polarization. You've made it into a dipole. A positive side and a negative side. That's what we mean by polarization. Here's an example. Here we have a charged balloon on the left. Now, how did it get charged? You may have rubbed it with fur, or rubbed it with silk, or rubbed it with something and drew out charges from it. So let's say we left it positive. Okay? The charged comb, where do they have a comb here? Attracts bits of paper. Oh, I'm sorry, these are two different things. If this is a charge like a balloon, let's take that balloon and rub it on my hair, say. No, I don't have much to do, but if I can find some. Rub it on my hair. Now that's if my hair is not too greasy and not wet, and there's not too much humidity in the air. And then I put the balloon on the wall, it'll stick to the wall. Because rubbing it on my hair rubs electrons off the balloon onto my hair, leaving it in positive charge. So the wall, which the charges don't move much, but the charges on the surface, the negatives go this way, the positives tend to go that way, just redistributing ever so slightly. This creates a polarization here. No charges are exchanged, and the balloon sticks to the wall. Okay, the other is I take a comb, usually a rubber comb my hair with it, and then if I have little scraps of paper on the table, I can pick them up. Why is that? Because when I comb my hair, if I had any, with the comb, I move charges around. And then that attracts the unlike charges go toward the comb, the like charges go away from the comb. That's attracted, but the next piece of paper, the unlike charges attract the like, and they just make a chain effect there, and it attracts bits of paper due to the polarization of the paper. Now, okay, we're going to stop there, but let me give you one more example of polarization that I wish I didn't know so much about. Have any of you ever heard of cobwebs? Guess what? They're not really webs. What they are little charged pieces of dust. And then a positive charge reaches a negative and a negative positive. They make these little strings that look like a web, but all they are dust. Fortunately, we have a few in our house, okay? And so a cobweb is an example of polarization. Okay? Not a very favorable one, but hey, one nevertheless. So we will stop there tonight, and next time we'll only go for an hour and a half. Once upon a time I had a pencil in here. I've lost it. Okay? Good deal. Paper topic. Good deal. Ah, here it is.
What are we turning?
What's that?
What are we
Paper
turning?
topic.
Oh, do we have to
these
turn
are
that in
from
today?
You don't have to, but
Okay.
bring it next
I'll
week.
think about it and turn mine
Those
in.
are from my other two classes.
Okay.
Yeah.
All right. I would get hopping on those rather than have them all wait till the end. Have a good weekend again. Next week we'll actually have 2 classes for a change. Okay, we'll pick up here in Coulom's Law next time.